All right, so let's take a look at this equation here. We have f of x is equal to 3 to the x power. Our base is 3, our exponent is x. So going back to the characteristics of an exponential function, our base, which is 3, that's greater than 1. So whenever we graph this function, okay, the graph is going to go up to the right and is an increasing function. Okay, so the greater the value of b, remember, the steeper the increase. So this is what our graph of f of x is equal to 3 to the x power. Okay, now if you want to, you can create an xy table. And better yet, we can even put this information into our graphing calculator just so that we can see. And let's clear that. So we can see what 3 to the x power looks like. So we have 3 raised to the x power. And we can look at the graph itself. Okay. And the graph mimics just what I have here that's been printed out here. And then let's go and look at our table. We have second and graph. And we can look at some values here. Okay, now here's the y-intercept at 0, 1. And as we look at this graph going from the left to the right, this line here, or as we read this graph from left to right, it seems like it's touching the x-axis here, but it's not. It's going to always come closer, closer, closer to the x-axis, but it would never actually touch the x-axis. So we have a horizontal asymptote, which is y is equal to 0, which is the x-axis. Okay, so being able to graph this, you can create an XY table, plug some values in for X. So 3 raised to whatever that power is. We have 1, 3 when X is 1. Okay, when X is 2, we have 9. And we can go to the left. Okay, so as I, looking at our table here, as I keep going, think about the graph on the x-axis to the left, you notice the numbers are getting smaller because this is going, it changed to scientific notation. So it'll never touch the x-axis, but it'll get close to the x-axis at 0. Okay, now what I want us to do is, and we've talked about transformation of functions, we've talked about the quadratic functions and absolute value functions. Now let's look at the exponential function. Well, we have here transformation of exponential functions. We have f of x is equal to negative a, or if there's a negative, we'll talk about that, but a times b raised to the x minus c. And what happens if there's a negative in front of the x? So what let me finish this off, plus d. This is the equation. Okay. Now, what you're used to, the vertical shift. Okay. If it's positive, if that number is positive, we move up that number of units. If it's negative, we move down. Now, where the horizontal shift comes in is if we attach a term next to the exponent of the variable x. So we're calling this C here. If that number is positive, we're going to move left that number of units. If it's negative, we're going to move right that number of units. So just like how we've been doing the horizontal shift in class before when we talked about the quadratic functions and square roots, all of that good stuff. With the horizontal shift, we go in the opposite direction. Now, if there is a number in front of this b, for example, here, let's say we go back to that function, f of x is equal to 3 to the x power. Let's say that there was a number in front. Let's say 2 times 3 to the x. Now, what we would not do is multiply 2 and 3, because here we have a factor of 2. Here we have an exponential expression of 3 to the x, so they're not the same. So if there's a number in front, what this is saying that it's going to either be a vertical stretch if that number is positive, okay, or it would be a vertical shrink if the number is between 0 and 1. And let me clarify the vertical stretch if the number is positive but greater than 1. Okay. Now, if we have a negative in front of whatever we call A, then it means it's going to reflect about the x-axis. So we talked about this information in class as well. Going back to the exponent of our base b, the variable x. If there's a negative in front, it's going to reflect about the y-axis. Okay, so we talked about the domain, um, the range, and we also talked about the horizontal asymptote. So you have all of that information on or in your notes with what is the domain, the range, and the horizontal asymptote, and how to find that. So let's look at this example here. All I want you to tell me, how does this translate? Here's the parent function. How do we transform this? What will we have to do? So the first example, we have h of x is equal to negative times 3 to the negative x power. Okay, so because there is a negative attached to the exponent of x, that this is going to reflect about the y-axis. And because we have a negative exponent in front of the base 3, it's going to reflect about the x-axis. So that's all I want you to do. Just tell me, how would these graphs change when we start adding numbers to the equation. B, we have g of x is equal to 3 raised to the x minus 1. Well, the x minus 1, or the minus 1, because it's attached to the or with the variable x that's as an exponent, we're going to have a horizontal shift, and because it's negative 1, we're going to move right 1 unit. C and D, we've already talked about that. There's really no need for us to really do a whole bunch. Remember, when it's in front, this is going to reflect about the x-axis. So C is f of x is equal to negative times 3 to the x. D, we have g of x is equal to 3 raised to the negative x power. So this is going to reflect, because the negative is with the variable x as the exponent. So it's going to reflect about the y-axis. And then let's look at f. We have h of x is equal to 3 to the x power minus 1. We have a constant term of negative 1. Therefore, this is a, not horizontal, but vertical shift. And we're going to move down Because the 1 is negative, we're going to move down 1 unit. All right, I want us to take a look at this graph here. Now notice that this graph that we have here, it says f of x is equal to e to the x power. Let's talk about this e to the x power, which is called the natural base e. Okay, so the number e, think of pi. Pi is a symbol that we use that has an approximation of 3.14, and it's an irrational number, where e falls in that same category. Okay, so the number e frequently occurs in mathematics, especially calculus, and is an irrational number. And like I said, like pi, its value is e is equal to 2.718281828, and so on. It's one of those um, numbers that keeps going. It doesn't stop. Where we would use E at, E is the base rate of growth shared by all continually growing processes. So we would use base E whenever it pertains to um, when we're talking about growth and decay. It We would use this natural base, and we would use this formula. E is the value of 1, the quantity of 1 plus 1 over n, all raised to the n power, as n approaches to infinity. So the natural logarithmic exponential function is f of x is equal to e to the x power. Now, these go hand in hand with the exponential function, but what's different from what we just covered is that our base for our regular exponential function is a number, okay, a real number, excuse me, a rational number, be it positive or negative, okay, excuse me, being not positive or negative, but being that it's between 0 or 1 and greater than 1. Now, what's happening here, what makes this natural base e function is that we have a base of e, okay, and same thing applies when we have a base e. We have a y-intercept of 0, 1. Okay, as we read the graph from left to right, it's going to be an increasing function, and it has a horizontal asymptote um, on the x-axis, which is y is equal to 0. So we definitely will be going back and forth, and we're going to be talking about common logarithms and natural logarithms in the next section, but I definitely want to just make note of the natural base e and how it parallels with the exponential function rule.